Okay, we're moving on to our final episode. I'll say hi. This is going to be on black holes, so 2 rounds. Okay. So, before I start talking about black holes, I think I left out something really interesting about gravity. So, just like how we saw when you go close to the speed of light, time slows down. Also, when you are in a gravitational field, time slows down as well. So, let's say this is Earth. So time is slower for you than your twin outer space and an astronaut in a little rocket. So yeah, so time slows down with gravity, and well, this is due to the curvature of space, but it's pretty analogous to going the speed of light. Okay, so obviously we can't go faster than the speed of light. So what's that analogous to? Well, it's analogous to a black hole standing right above the black hole. So when you go, as you approach the speed of light, time completely stops for you compared to your twin on Earth. So 1 second for you would be an infinite amount of years for your twin on Earth as you go very super close to the speed of light. Like you can't get any closer to the speed of light. Time will be infinite. And same when you're in a black hole. So like I said, the Earth collapses to a black hole once it gets in a very small size. We'll see that exact size, and then time pretty much slows down. So I'll tell you the result. The size the Earth has to be is this is Newton's gravitational constant. I think it's like 10 to the minus 11. You should check it. Don't quote me. Then the mass of the Earth, and then the speed of light squared. Okay, so the mass of the sun, since it's a lot bigger, it could fit in a bigger area. The radius, remember, the radius is something 3 times pi. So that is the volume of a sphere. So is it pi squared now? I think it's pi cubed. Sorry about that. Or r cubed. Okay, that's the radius of the sphere, or the volume of a sphere. And now you have to get the Earth of the sun into this the whole Earth into this volume. So we calculated this from last lecture because this was how we modified our equation. This is more it looks better. So just like how we multiplied to get the Big Bang, we multiplied by a factor of a. Here we divided by this factor, which you could learn about in the previous video 3.5, and we found that when we're at this radius exactly, we plug this in, and then compared to somewhere on Earth, you are not moving any time, and the distance is infinitely long. Also, when you're going close to the speed of light, you'll also see length get shorter. So I didn't cover this effect, but for you, maybe like something like 5 feet would be 1 foot if you're going close to the speed of light as you're there. Okay, so we have this interesting formula that we proved in the last lecture. This will give us a black hole, the effects that we want, where as soon as we go near the black hole, time slows down so much. It's pretty much time is frozen. What's interesting is when we go into the black hole, which so the person from the outside, okay, we'll see this later actually. So anyway, so let's look at about how big this is. So let's get a scale. Okay, actually I wrote down the gravitational constant here. So if we plug this in, the mass of the Earth is this, plug it into here, plug it in here, plug it in here. So right now, this is the current speed of light. This is the gravitational constant. So this is the current radius of the Earth. So it's pretty big, almost 4,000 miles. And once you calculate this, you'll see that the Earth has to go from 4,000 miles to about half a centimeter. So, or 1/4 the size of a dime to be a black hole. So yeah, that's go really small. And you could also become a black hole too if you get compressed small enough. So if you weigh 75 kilograms, you have to squeeze into this amount of area to become a black hole. And then as we see, the person outside the black hole, it pretty much takes an infinite amount of time for this person to cross the black hole. So this person never sees his friend cross the black hole. And in fact, there's some theories which the person never crosses the black hole. He just pretty much burns at the event horizon. You can look up, it's black hole complementary. But if you go through the black hole, he won't see anything strange. He'll just pass through pretty smoothly in a short amount of time. And then it only takes like a micro fraction of a microsecond for him to go from the event horizon to the singularity, where we don't know what happens. So this is a mystery that we still have to solve, but there are a lot of interesting speculations. Okay, oh, so 6 microseconds, not a fraction of a microsecond, my bad. Okay, that's the reason. Yep, so nothing can escape a black hole. Okay, this is, so light, so it takes, just like how it would take an infinite amount of energy to go faster than the speed of light, it would take an infinite amount of energy to come out of a black hole, and that can't be possible. And light can't even escape a black hole. So this diagram is a little interesting, and I think I could convey it to you with a little explanation. So light travels, okay, with space, and this should be time times c. Okay, this looks a little daunting, but I'll explain this to you. So this is pretty much the path of light. So light travels at 45 degrees. You could see this pretty simply. You just write down what we've been doing the whole time, times c squared dt equals ds. And I'll leave it up to you to figure out that light, oh sorry, these are triangles, not d's. So d stands for delta, and triangle also stands for delta. The difference is a little bit, but it's not that. It shouldn't be too scary. So anyway, I'll leave it to you to figure out if light is only moving in the z direction. So I'm taking triangle y equals triangle z equals 0. Then I'm taking, this is the east direction. So if light is only traveling in the east direction, prove that light always moves 0 space-time distance. Okay? And 0 space-time distance on this graph is just 45-degree lines. I'll give you a hint, divide by t, dx squared dt. And so this whole thing squared is just delta x squared, delta y, or delta t squared, but I just wrote it in. This is going to erase a lot of it. Okay, just ignore that. Just ignore this little factor. Minus c squared equals ds. So if you don't know, if you don't understand this, if you don't know why the ds equals 0, look back to the first lecture. So anyway, this is a 45-degree line. You could see that this is the slope. This path of ds is a slope of 1 in flat space. So it has a constant slope. Okay, so then once the effect of the black hole, once the black hole produces a gravitational field, then space starts to get curved, and these are all lines of ds 0, but it's not 45-degree lines anymore, which you could literally, in order to see that, if you really want to play with it, you could go back up here and set this equation to 0, because light travels 0 space-time distance. So you set this equal to 0 and then compute dx. You could set these equal to 0 as well, and then compute this thing. Well, not this one, because I set r equal infinity here, so you would do it with this one. Okay, great. So let's get to some interesting conceptual things. So anyway, so light keeps traveling these paths of 0, and then once it hits the event horizon, the path of 0 space-time distance is just motion through time. And then the path of 0, and these are when the light shoots outward. So if you flash a light away from the black hole, these are the paths it will take. And then if you're at the event horizon and you shoot the light away from the black hole, it'll get stuck at the event horizon, and then so it won't move because it's like literally like the 0. It's fighting the black hole's gravity. It's fighting the pull of the black hole so much where it cancels each other out. Or you could think of the event horizon as a place with 0 that doesn't move through time or space. So both are very interesting. So anyway, if you cross it, then both like in out. So if you shoot the light out, then it will still go into the black hole, into the singularity. Okay, and this is 0. So actually, this is the singularity. Sorry, I put the black hole right here. The black hole should actually be covering this whole thing, because that's where the black hole is, and this is the singularity. But I could just explain that to you now, and I'll give the purpose. Okay, so cool light rays are fighting the curved space, and then obviously once it goes past the point, once it like completely gets past the point of the gravitational field, it then becomes a 45-degree line. So it fights gravity until it leaves the gravitational field and becomes a 45-degree line. And no matter what, the gravitational field depends on the mass. So even if the Earth is a black hole or it's 2 times its size, right now the person here will feel the gravity. It won't tell. It'll feel the gravity the same way as if the Earth was a black hole or it was the same size or twice the size or 3 times the size. I mean, given that the size of a black hole is still, you're not inside the Earth. So, okay, that's just an interesting aside. Okay, so we saw this. So every time mass falls into a black hole, so every time anything falls into a black hole that has mass, it grows because what's inside the event horizon, whatever, even if there isn't inside the event horizon, this is, like I said, conceptually not understood at all what black holes are, so that's why they're so interesting. So anyway, so there's a mass associated to the event horizon, and then as things fall into the black hole or get trapped on the surface of the black hole, this mass increases. So then, since the mass increases, the black hole increases. So we could see that by this argument, but can the black hole shrink? And it's yes, and it shrinks in a very interesting way. This is the reason why Stephen Hawking is famous. So it radiates as if it's very hot. So just like we radiate, just like your furnace, it radiates particles. The black hole radiates light, a bunch of particles, electrons, everything. The black hole just radiates. So pretty much, in a sense, produces these particles and everything. But yeah, so we know that radiates, okay? And if it radiates, it must have a temperature, because things with temperature radiate. And it's kind of weird because, okay, like we see, okay, our furnace, our heater, like these things radiate. I mean, even us, the table is radiating. We're trying to become in thermal equilibrium with our outside. We're trying to be thermally equal. But it's kind of weird that space would do this itself. So, but yeah, so black holes have a temperature. That's even weird. And yeah, these are things that, okay, like why do black holes have a temperature? What we consider temperature now is just if we have like a pot of water, we say the temperature of the water is just how fast the H2O molecules are moving. So like what's the tiny description? What are the H2O molecules equivalent of the black hole? That's very, very interesting. And there's some explanations that I won't go into that involve string theory. So I'll give a little bit about string theory later. So the hotter things are, the more they radiate, of course, and Okay, I could also go into another quantum explanation of this, but we'll keep going, and maybe I'll do it at the end of the lecture. So the temperature of the black hole is actually inverse to its mass. So the larger it is, the more massive it is, the lower temperature it has. And then the lower the temperature it has, the less it radiates, because there's less, it's not as hot, it's not radiating. There's less temperature difference. So big massive black holes are colder and they radiate less, and then smaller black holes lose mass faster. So small black holes are very unstable compared to big black holes. The black hole the size of the Earth, which is, like I said, only like a half of a centimeter, is this much years. It'll take this many years for the black hole to evaporate, and the universe will probably end way before then. However, the size of a human it only takes a very small amount of time, like almost pretty much instantaneously, for us to radiate away. So this is very interesting. These are very interesting points. Okay, so there is kind of an issue that we have, and I'll explain this. So once the radius of the black hole gets to this, Einstein's theory breaks down. And in fact, more profound is there's no way we could even measure something this. We could even make measurements on distances less than minus 35 meters, because the smaller we go, the more energy we have to use. So let's just say, okay, so when we play with particles, we have these huge particle accelerators, and then they take a lot of energy to smash these two particles together and look at scales. I'm not too sure at the top of my head, but maybe like 10 to 16, negative 16 meters. So that is and we need a lot of energy, so much energy. These mile-long accelerators, just packed with energy, could only get us to look at physics this length. However, if we pack as much energy if we get enough energy to see physics at this scale, we'll put so much energy into a tiny amount of space that it will create a black hole itself. So this is the universe telling us we can't look at this distance. We as humans can't do any experiment that will tell us what is below this scale, and Einstein's theory breaks down. This is, we need to get into something called quantum mechanics to deal with this scale, and then I'll explain actually Hawking radiation too right now. I said over here there's involved quantum mechanics. So the thing about quantum mechanics, you could actually look. I posted a video about quantum mechanics. I'll put the link below. It was a while ago, a couple years ago, so I look a lot different now. So in quantum mechanics, particles could pop in and out of existence. An interesting experiment you can look up is the Casimir effect. So we know that positive particles attract each other. And then, positive and positive repel, negative and negative repel, positive and positive attract. But about two neutral objects? So two neutral plates together in a vacuum, what will happen? And you would think, okay, they're not neutral, so they won't attract or repel each other. What actually happens is that particles pop in and out of existence on the inside of the plates, and particles pop in and out of existence on the outside. And technically, an infinite amount of particles are popping in and out of existence on the inside and on the outside. And both on the inside and the outside, infinite amount of particles are popping into existence. But there's more infinite. It's a higher infinity of particles on the outside than on the inside, so there's a pressure. The concept of having one infinity bigger than the other is weird, but you could just think of it as infinity plus 1 will be greater than infinity. You could always add. So, like I said, this is a weird thing. So this is a cool effect called the Casimir effect. yeah, I was going to say something. Let's see. Okay, but yeah, this effect happens at 10 to negative 9, so that's where quantum effects pop in. Okay, so that's why I'm like quantum, so we don't have a quantum theory of gravity. That at this scale, this is where quantum mechanics should play a role in gravity. So we don't have that yet. You might have heard of string theory. That is one of the theories of quantum gravity, and it provides an interesting picture of what happens when we get below the scale that we can't see. So, okay, what is string theory? So we have points. So let's just say the electrons are points, like these particles, the proton, the neutron. Well, the proton and the neutron are made up of 3 points. And then light could just be a point. So string theory replaces these points. I mean, this isn't even a point because this has like some width. I literally, it's impossible to draw a point because even there it has some width. No, like actually like one, like no radius, just an actual point. So that's right now, that is what we perceive these particles to be. That's how we model them. However, string theory says, okay, they are actually one-dimensional strings, and they make sense when they're about this length. So they could be open, and then if they're open, they land on things. And open strings are responsible for light and stuff, and then they could be closed, and this is kind of responsible for gravity and such. And open strings could close on each other if the 2 endpoints meet, yada yada. Okay, so what's interesting is so all these different particles, they have different properties, but they could all be expressed as the same string. So just off the bat, we see, okay, we learn that different particles have different masses. Well, the different masses actually correspond to how the string vibrates. So the lowest mass, so 0 mass, is just 1 vibration like this. The string just goes like this. Then the next higher mass is this. So depending on the particle's mass, you could say, okay, if this many vibrations, it vibrates this much. And some particles have charge, so the charged particles have to be open strings because these endpoints are called brains. I'm making them look like dumbbells, but really these brains are pretty big. There's some charge on there. So they pick up charge from the endpoints that live on these. You could even think of the brains as some type of quantum space they live in. But then the picture, okay, I'll take back that statement until further notice. Okay, but yeah. So, okay, what does it say about black holes evaporating to so if a black hole evaporates so much and then it gets to this radius, what will happen? And then so string theory says it just turns into a really massive string. So like we said, like the mass has to do with vibrations, so, or a very massive particle, so it's just a particle with a bunch of vibrations and a lot of mass. So in this picture, we have these strings becoming black holes, and these black holes becoming strings. So it's very interesting. Also, another interesting thing that string theory suggests is that our universe is a hologram. So, and this idea comes from the black hole. So understanding what is inside of a black hole, that's, like I said, it's a very interesting area of research right now. So all we could say is that there's an event horizon, and the event horizon is kind of like a 2D surface covering this 3D black hole. So, okay, so this is not a face, even though it looks like a face. I'll draw this guy with a tongue sticking out, 2 eyes. I'll roll with it, but I drew this to become a black hole, and the surface of it, like I said, is 2D. So by this analogy, we could say that, okay, maybe this 3D world that we live in, or 4D, is modeled, well, time. Okay, let's say this 3 spatial dimension world is actually covered by a 2-dimensional spatial world. And then this actually gives a deeper relationship between electricity and magnetism and gravity. So electricity and magnetism, we already have that. Okay, these equations look similar. And then we have like GM, this is GM, M, and this is KQQ. So right now it's like, okay, at this level we see some similarities, but then once we get closer and closer, we see these gravity and electricity are actually very different. In fact, there's 4 forces, and then one of them is the strong force, one of them is a weak force, and these are responsible for holding the atoms, or holding we have a proton, and the proton's made of 3 different particles. So those are responsible for holding the proton together. That's a strong force. The weak force is responsible for radioactive things. The electric force is responsible for electricity, and I'll just put the weak, so the weak strong electricity force could be put together and pretty consistently, and then the gravity force cannot, it's separate, it's a separate entity, and we described it in detail in this lecture series. But the holographic principle has a way to encode both pieces of information. And it's saying that, okay, these electric fields on the boundary, or on the 2D surface, okay, so electric field on 2D surface produces gravity inside of this, inside of the analogy of the black hole. So inside the universe, we get gravity because we have some 2-dimensional surface on the outside of our universe that has these other fields. So that's kind of how they are connected. That is one route of connecting the two. There's a lot of interesting things. You could check out the holographic principle, please. Yeah, you might learn a lot more from people who study this on YouTube than my casual reading. So thank you. It's been fun. It's been a good journey. So I'll say sayonara. Peace out. Okay, I need to now close this out. Okay. Bye-bye.